It's a
Hey, are you doing the recording? Are you doing Monday also, the review session? Next Monday.
probably, yeah.
Okay, because I might be gone, so I'm looking forward to the. Yeah, thanks a lot.
I'm gonna blame it on Larry. He dropped the ball. He took it over and then stopped my jokes. So I'm gonna tell like 6 today.
By the way, the jokes will be on the bed.
That's true. We have a lot, so I'm just gonna tell the ones that I already sent while we weren't telling them. So I'll tell 3 now and then maybe 3 straight. So I don't remember who sent these to me, by the way, so if you're brave enough to take credit for it, please do. But we have a website. I don't know if you've seen that. On our course website, there's a jokes link, and then there's all the jokes. How does a hungry computer scientist look for food? Bread first served.
Bread.
That's pretty good. Don't laugh so loud, it's okay. How many support vectors does it take to change a light bulb? Very few, but they must be careful not to shatter. Okay, and the last one I'll tell. There are 2 kinds of statisticians. First, the kind that can extrapolate from limited data. All right, so not quite as popular as our previous ones, but it's a good start. We're back on jokes. So last time we kind of wrapped up convexity of functions, and we went through in pretty good detail the last 2 lectures convex sets, convex functions, their properties. We went through operations that preserve convexity, so how do I transform convex functions and still get convex functions? Equivalent characterizations like this one, which says that if we have a differentiable function f, then it's convex if and only if the first order Taylor approximation to f underestimates the function everywhere. Okay, this is like I take a Taylor expansion, this is just the linear term. That's a global underestimator of the function, then that's an equivalent condition for the function being convex. So I just drew a picture here. Okay? So this is the point x, and the corresponding to that equation, and that's the function f. And if I look at any other point y, say I take y out here, then the construction from the first order Taylor approximation on the line has to lie below the function. So that's equivalent to f being convex as long as f is differentiable. And we also saw why this was important, why convexity was important, why I've been spending so much time on it the last couple of lectures, was that we wrote down an optimization problem. We defined what it meant for that problem to be convex. Remember, our optimization problem is the form minimize some function subject to a bunch of constraints. Those constraints are of the form other functions being less than or equal to 0 and other functions being equal to 0. And so that the problem is convex if the criterion, the one we're trying to minimize, is convex. The inequality constraint functions were convex, and the equality constraint function had to be affine. That's what it means for a problem to be convex. Okay, that's a very broad class of problems. And what we saw was that convex problems do not have local minimizers in the strict sense. So it means that if I find any point that looks like in some local neighborhood it's optimal for one of these problems, it has to be globally optimal. And that was the real compelling reason to focus on convex problems, was that we're never going to fool ourselves by kind of going downhill and finding some point that looks locally optimal and then stopping, because for a convex problem that's good enough. Local optimality is the same as global optimality. Okay. Any questions about what we learned in the last couple of lectures? Yeah.
So the point of studying all this, so that if we've got a new problem and it's unrestricted and we have the chance to choose restrictions, we then want to choose restrictions on as we get a complex problem so that we know we're going to solve it. Is that why we do it?
A great question. So it's kind of hard to tell you how to master kind of the trade of designing optimization problems in just a few lectures. We try to do a little bit more of that in 725, of course. But I'd say the point, as of right now, is to allow you to look at a problem and determine whether or not it's convex. And if it is convex, then you can already apply kind of all these algorithms that are de facto standards for these to this problem, and know that you won't be in trouble by finding a local minimizer. You can take the KKT conditions and characterize the solution. You can study it statistically because of that. If it's not convex, then it's kind of hard to convey to you in just a few lectures what you can do. But oftentimes we can actually re-express a problem as a convex one, either as a good approximation or just as an equivalent problem. And so that's kind of a bigger picture. But for now, I think it's just, you can think about it as a tool. It allows you to identify convex problems and then apply all your algorithmic and statistical tools to it. Any other questions? All right, so today we're going to talk about subgradients to begin with, which I said last time, it was like calculus for grad students. I still think that's a good analogy. And then there's a lot of other stuff in notes we're not going to cover. I just wanted to give you some, a kind of a unified place to look in case you're interested. I think my plan is going to be to cover subgradients, to discuss what we call first-order methods. These are algorithms that only use the gradient or gradient-like information in order to minimize the convex optimization problem. And then to talk about the KKT conditions. So I'm going to skip duality entirely. Duality is a very pretty subject, it's very useful, but we just don't have time for it. Usually it's given, at least the way I've taught it in the other course, we use it to prove the KKT conditions, and we use it as motivation for the KKT conditions, but I think it's not really crucial. It's all in the notes in case you're curious. All right, subgradients. So this is a good place to start off when we talk about subgradients, is this characterization of convex function, because we basically start with the same definition, and we just modify it to define a subgradient. So if you give me a function, then a subgradient of my function f at a point x. So this function, by the way, at this point it need not be differentiable. It also need not be convex. So it's just a function. Just a function from Rn to R. I define a subgradient of a function, f, at a point x, as some vector g, just a vector g that satisfies basically this equation where I replace the gradient by g. Is that if I look at the line that's emanating from x or passing through x, that's defined by this direction g, that this has to provide a global underestimator of the function. So for all y, the function is bigger than or equal to the value that is constructed from that line. So if f were convex and differentiable, then we know that a subgradient at x is just the gradient. Right? We know that this property holds when I take g equals the gradient of f of x. But the idea of a subgradient is much more general than that. And so I can have for example, if I look at the absolute value function, I want to start off with as to get a sense of what's happening. If I ask for subgradients of this function, so this is just f of x equals the absolute value of x. We actually tend to call this a subderivative because it's just in one dimension, but I'll just keep calling it subgradient just without kind of concern for that. So let's pick a point x. If x is positive, then a subgradient of f of x is just 1. In fact, it's the only subgradient, right? Because that's the only value of the slope of the line that I can have that's going to underestimate the function. So it's actually, when x is bigger than 0, the subderivative is just the derivative. When x is less than 0, it's the same thing. The subderivative is just minus 1. There's only one of them, and it's just minus 1. When x is equal to 0, we're kind of in a different story. And actually here, I can take a bunch of subgradients. What are the set of subgradients of this function f when x is equal to 0? Yeah, actually, so g, the subgradient, can be anything in between minus 1 and 1. Right? Because that's because if I take any line with slope equal to g between minus 1 and 1 that passes through 0, it still provides a lower bound on my function. Okay, so what we write is, we write this partial f sign, partial f at point x, as the set of all g, such that g is a subgradient to f at x. So this is called the subdifferential. It's the set of subgradients at x, called the subdifferential. And what we've just shown is that when x is bigger than 0, the subdifferential is just the set containing 1. When x is less than 0, the subdifferential contains minus 1. And when x is equal to 0, the subdifferential is the interval minus 1, 1. Anything between minus 1 and 1 provides us a valid subgradient. So here are some properties, by the way, of this guy, which I said we call the subdifferential. The first one is that for a convex function, the subdifferential at any point x is never empty. So what that means is that at any point x, there is always at least one subgradient to f at x, if f is convex. Okay, that's not obvious from our characterization from convexity. We know that when it's differentiable, that's true, because it's just the gradient. But even when it's not differentiable, there's always at least one subgradient at every point x. It's a very nice property of convex functions. Okay, here's another one. For convex differentiable functions f, this one's kind of obvious enough property if they're the subgradient of f at x is just the set containing the gradient. And conversely, if the subgradient of just any convex function, the subdifferential just contains one point, then this means that g must be the gradient of f of x. So it actually provides us a way to check that a convex function is differentiable. If I have a convex function and I look at all of its subgradients at a point x, if it happens just to be one of them, that actually proves that the function is differentiable at that point, and that we found its gradient. Okay, these are all properties I'm just writing down. I'm not proving them for you, but they're all properties of subdifferential.
The first one is
This one? No, non-convex functions can still have subdifferentials. So an example would be a function kind of like this, right? Rather than these 1 off to infinity. I still have a subgradient here, but it's not a function. At every point. Yeah, I think so. I think that's true. Because the way we prove this, as Larry was kind of saying, is that we use the supporting hyperplane theorem. And I think that the converse of the supporting hyperplane theorem is true. There probably has to be some conditions on F, because there's some conditions for the converse of the supporting hyperplane theorem. But I think under some conditions on F, it's true. That if I have it being on empty for every point, it's convex.
Is there also a local definition of separating? Say if I want to minimize a non-convex and also non-smooth function, is there an analogy of the global definition of separating in that sense?
Non-convex, non-smooth.
Yeah, if I want to use separating in sense to minimize that, but for certain points in the function, the separating doesn't exist. Suppose all I carry is a local minimum.
Yeah, I don't know about that. I'm not sure. I don't know how you would prevent yourself from entering regions of the input domain where the subgradient doesn't exist. Seems like if you were to
But
try to
if
use
the
something like,
separating is defined in the local neighborhood, then
yeah, I don't know. Good question. I'll think about that when we write down subgradient descent. But I wouldn't know how you would avoid yourself from moving into a region where the subgradient is not defined. So you probably have to be careful somehow to choose the step size or something.
Even if you define it on a local neighborhood, how easy would it be to compute it? Whereas it's for convex functions, it's fairly straightforward.
Well, it's typically an analytic thing. So I think it's probably more on a case-by-case basis. Even for convex functions, it can be very difficult to compute subgradients in some cases. You just have to kind of understand the analytic properties of the function. But so this last property I wanted to bring up, this last property, which, let me say, F is convex. If the subgradient contains one point, then it's differentiable at that point. That can be used to prove that a lot of convex functions are differentiable, but are really non-obvious. One example is we can prove that the function that maps point x to its distance from a convex set C. So this was, it's going to be the minimum over all y and z of x minus y. If I call this f of x, then I can prove that this is differentiable by just taking its subgradients and showing there's only one subgradient. And there's a bunch of other examples as well. So it's a nice property to remember. It's another way of proving differentiability for a function, convex function. For a non-convex function, we kind of said this in words. I'm not going to write it down, but subgradients still can exist, but they need not exist, even for a smooth non-convex function. So we had this example last time, like x cubed, for example. Right? There's no subgradient of that function at 0. And as far as I can tell, a theory for subgradients of non-convex functions is not nearly as well understood. One other property that's interesting, and it's going to kind of reflect a bit to some of the properties that we see when we talk about the KPZ conditions. And if you were to study duality, you'd see kind of this thing in duality as well, is that the subdifferential is always convex. And this is true regardless of F. So if F is convex or if it's non-convex, it doesn't matter. The set of subgradients of F at a point x is always a convex set. It's a pretty unique property, but it's very easy to check that. Just plug in the definition of a convex set, and you can check immediately that that's a convex set. Okay, so we already did the subgradient of the absolute value function. Let me just do a couple more examples. I'm just going to do 2 more examples, actually. The first is the L1 one. And we're going to characterize its subgradients, and then I'll do one other example. So let's look at the L1 norm. And then try to characterize elements of the subdifferential or subgradients of F if xi is positive, then it turns out that for any subgradient, the ith component of that subgradient, remember subgradient is a vector, right? If f goes from Rn to R, it's a vector Rn. If x is positive, then gi is equal to 1, uniquely. Any subgradient has to have 1 in its ith component. If xi is negative, then gi must be equal to -1 uniquely. And if xi is 0, then we get the same thing as we got in the one-dimensional case, which is that gi could be anything between -1 and 1. Okay, so that's a characterization for the subgradients of the one. Any questions about that one? That one's going to be useful because we're going to revisit this guy when we talk about the KPP conditions. So another way of writing this is that gi is just equal to the sine of x if xi is not equal to 0. Otherwise, it's just between -1 and 1. Okay, one other example I want to do real quick is another one to give you a feel of what happens when we take maximums of functions. So let's suppose that I have this function f, which I define as the maximum of f1 of x and f2 of x. And let's just suppose that f1 and f2 are differentiable. Okay, and convex. Taking the maximum of two differentiable convex functions. Again, there's going to be actually 3 cases for the subgradient. See if we can guess them here. All these you can prove from the definition, but I think it's helpful just to think about them intuitively, make a guess, and then venture an attempt at the proof. So if let's look at a region where I have x values such that f1 of x is strictly larger than f2 of x. What do you think the subgradient is? Draw a picture here. So let's suppose this was f1, that was f2. They're differentiable convex functions. I just drew their extensions here, but I'm taking the maximum to them, so I get this function, and that's f. And now I'm in a region I'm telling you where it turns out that f1 is strictly bigger than f2. So I want to know something like the subgradient of that function, the maximum function at this point x. It's what? Yeah, subgradient of f1. That's right. But then what's, if it's differentiable, that's just, it's just the gradient of f1, right? The g is just the gradient of f1. All I need to do is do this guy, and if it lower bounds f in that region, then that's good enough because f is bigger than f1 is bigger than f2. And likewise, if I have the value of x such that f2 is strictly bigger than f1 of x, then the subgradient is just f2, the only subgradient. And now here's the tricky part. It's the only tricky part. This is the only point at which the function's not differentiable, right? Potentially, is where I get the values of x for which they're equal. If I look at x such that f2 of x equals f1 of x, then what are the set of subgradients for this function, the maximum function? That? The cone. What is the cone generated? By the gradients. Close. It's very close. It's not quite a cone though. Let's look at the picture here. What's there's kind of 2 extremes I can take, right? All these are valid subgradients, but how far can I go in one direction? Let's say how far can I go in this direction of the positive slope? I can go no farther, right, than the gradient of f1 at that x. And in the other direction, I can go no farther than the gradient of f2 at that y of x. Right? If I go farther than that, in the positive direction, the negative direction, then I no longer have the lower bound property. So in one dimension, it looks like, it's the interval between the derivative of f1 at x and the derivative of f2 at x, right? So whatever is the smaller or bigger, I take that interval. And it actually, in higher dimensions, it just ends up being, it's the line segment that joins their gradients. Okay, so I just compute the gradients, and anything along that line segment, take the convex combination of their gradient vectors, that's a subgradient of this function. Okay, and what we're going to see in a second that this property for subgradients of maxima can be extended substantially. Any questions? Okay, so I'm going to breeze through some properties here so that we have time to talk about algorithms, but I think when I get to the last property, you're going to see why subgradients are also a very important notion for us to care about. And the last property is absolutely trivial, but it's a bit unexpected, I think. Okay, so some key properties is that if I have, so in everything I write down, I'm going to assume f is convex. We're just going to talk about convex functions because that's really where we understand the most about subgradients. So if I take alpha times a function f, and I ask for the subdifferential of that guy, the set of subgradients of this guy, then provided that alpha is positive, that's just scaling the subdifferential of f of x. So the set of subgradients of alpha times f is just alpha times the set of subgradients. And if I take two functions and I ask for the subgradient of the sum, it's just the sum of subgradients. These properties are probably to be expected, pretty basic properties. Here it's important that alpha is positive, right? Because if alpha was negative, then alpha f would no longer even be convex. It'd be concave if f was convex, and so this wouldn't necessarily need to have subgradients. This is about the closest we get to the chain rule, this next one, with subgradients. If we try to go beyond this, then it gets quite difficult, but this is a pretty easy property. If I have a convex function f, and I define my function g by f of ax plus b, where A is a matrix and B is a vector. So I compose f with an affine function. Then the set of subgradients of G at a point x is just A transpose the subgradients of f at the point ax plus b. Okay. It's like the chain rule, but for subgradients. It would be the same thing if these were gradients. I'm sorry? No. I can always compose f with an affine function and it's still convex. There's no restrictions on that matrix. If this were like a quadratic form or something, then we'd have to worry about it being positive, definitely. Okay. Here's an extension of that maximum property I'm just going to state it in the most general terms we have, but there's a kind of intermediate version of the notes that you can take a look at. Let's suppose that I had convex functions f sub s of x, where s was just some index that lived in some set capital S. So this could be discrete. I could have functions, say, f1 through fm. So this just the number is 1 for m. This could also be infinite. It could also be uncountably infinite. I could be indexing tons of functions. I'm just going to index functions like this arbitrarily. And we're not placing restrictions on the size of s. And I'm going to define f of x to be the maximum over all s of fs of x. Remember, we already convinced ourselves last time that this was still convex. Even if s was uncountably infinite, it's still convex. And now we're going to look at the subgradients of this guy. And so here's the set of subgradients of f at a point x. I'm going to write equals. In the notes, I write down that there are some conditions under which we actually get equality. Usually it's just a containment. So you can take a look at those conditions. But those conditions are not very strong, so this is usually an equality. And I'm going to try to build it up from the inside out. So first, I look at all functions s such that f of s is equal to f of x. In other words, I look at all of the active functions. So these are functions that achieve the maximum at the point x. And I take their subgradients at x. And I take the union. So I look at all functions that are active, they achieve the maximum at that point x I'm trying to query for the subgradient. I take their subgradients, I take the union. Am I done? Is this the subgradient now? From what we know already, this can't be right. And there's a reason why. I may have erased it. So I shouldn't be expecting you to remember what I'm trying to get you to hint at, but this is not necessarily a convex set. We know that subdifferentials are always convex sets. So we know that I have to take the convex hull of this, at the very least. Okay, so that actually, under some conditions on f that are pretty weak, this is the subgradient of that. And so think about that case where I have to have two functions. It mirrors this exactly. It's either when x has the property that f1 is bigger than f2, and only f1 is active, and I just take the union of its subgradient, or its subdifferential at x, but it's differentiable, so there's just one point. That's the gradient. And so I take the convex hull of that one point, I just get that one point. That's what this is right here. Same with this case. Now when they're both active, I'm taking the union of the gradient of f1 of x and the gradient of f2 of x, and then I take the convex hull of that. That just ends up being the line segment joining those 2 points. Okay, so this is the most general property for subgradients. And for subgradients of maxima functions. And I'll use this real quick just to convey to you the power of that representation. Now we can compute subgradients of LP norms for any P. So that ends up being quite useful. So I'm going to have to rely on something called the dual representation for the LP norm, which I won't prove to you or discuss, but it's covered in the notes there in the duality. But it turns out that I can always take the LP norm for p bigger than 1, and I can write it as the maximum over all vectors y that have q norm at most 1. So these are vectors y that are in the q norm unit ball of y transpose x. And here, Q is a special choice of norms such that 1 over P plus 1 over Q equals 1. When this happens, the LP and the LQ norms are called dual. So the dual of the L1 norm is the L infinity norm, because I have to have the property that 1 over 1 plus 1 over Q equals 1, so I take Q equals infinity. Any P bigger than 1 is going to have such a complementary index Q, and then we call it its dual norm. So this is a representation I can actually always make for any LP norm P bigger than 1, bigger than or equal to 1. And now I want to compute subgradients of this function f. Well, using this representation, it's actually possible to do so. We see that a subgradient of f at x, I'll just write it as the LP norm at x, is just any vector y that has Q norm at most 1, and has the property that when I take y transpose x, that has to be largest over all such vectors y. And so I can write this must be equal to the maximum over all z that would be the subgradients of the LP norm. I can also just write this as so an exercise would be to think about the L1 norm, think about its dual norm, which is the L infinity norm, and then use this to derive the subgradients of the L1 norm we wrote down before. We kind of argued them this from our intuition before, and they were correct. This is another way to get the subgradients of the L1 norm. Think about which vectors that have an infinity norm less than or equal to 1, so that live in a box where each component is between -1 and 1. And have the property that when I take the inner product with the vector that I am querying, x, it's the largest possible over all such vectors in the box. You'll see exactly that I get the sign. It's just the sign of x in each component when xi is not 0. Otherwise, it's anything between -1 and 1. That's another way to look at it from this perspective. Any other questions? So here's a really nice property of subgradients, which is I think a real big supporting reason why we care about them so much. And like I said, it's completely trivial. And it's surprising, I think. Is that if I have any function f, then the following holds. X star, this function x minimizes f if and only if 0 is in the subgradient or is in the subdifferential of f at x. So if 0 is a subgradient of f at x, then we know that x minimizes that function. That's actually true for any function f. This is an arbitrary function. It can be convex or non-convex. It does not matter. Here's the proof. So what does it mean for 0 to be in the subgradient or in the subdifferential of f at x? This is the same thing as saying that if I take any point y, and I look at f of y in comparison to the value of y constructed from that first order approximation, then I have to have f of y is bigger than or equal to f of x plus the subgradient transpose y minus x. So that's just f of x. Right? It's completely trivial. So this just says that f of y is bigger than or equal to f of x for all y. It's equivalent to 0 being in the subgradient. 0 being a subgradient of f of x. Very powerful property, actually. Because now if we understand subgradients, at least for convex functions, then we know they exist everywhere. And so I can characterize minimizers by just checking that at the point in question, 0 is a subgradient. So let's use that actually right now to prove a form of a particular minimizer that's going to be useful to us in a bit. Let's consider the problem. I'm going to write it now in terms of beta. You'll have to excuse me, I'm a statistician by training, so I always come back to this. I'm not going to use x. Let's look at this simple least squares problem where I penalize the least squares term with an L1 penalty. So you give me y, I'm going to find beta that is closest to y in the least square sense after I add lambda times the L1 norm of beta. So this is like doing a lasso regression, but I don't have any predictors here. The predictor matrix is the identity. So actually, from what we have so far, we can characterize the solution to this guy explicitly. Probably a lot of you know the solution already. But we're going to use that characterization, which says that beta minimizes this guy, which I'll call f. Beta minimizes f if and only if 0 is in the subgradient, 0 is a subgradient of that criterion at beta. So let's first take the subgradient of this criterion using the rules we know already, and we'll just write down what a subgradient looks like of that criterion. So at arbitrary point beta, what's a subgradient in this criterion? So I want to take the subgradient subgradient of this. What's my first step? Well, I mean, there's a bunch of places we could start, but first we know that these two functions are both convex. I can split it up. So I can really ask for subgradients of this plus subgradients of that. And moreover, this is positive, so I can ask for subgradients of this plus lambda times subgradients of that. Okay, I'm going to get rid of the set notation actually because I don't want it to be too confusing. Remember, this is f, and I'll just write it like this. I'm going to just give you the form of an arbitrary element of the subgradient. So what are subgradients of this guy? It's just a gradient. This is differentiable. What's the gradient of that? Y minus beta? Beta minus y, yeah. That one I'm going to attribute to the fact that I've been talking for 45 minutes. Not that you didn't know that. Beta minus y plus lambda times the subgradient of that. We'll just call this guy, let's call S now. Where S has the property that Si is equal to the sine of beta I, if beta I is not equal to 0, otherwise it's anything between minus 1 and 1. So this is an arbitrary subgradient of that criterion. Beta minus y plus lambda s. Now we want to try to find some beta that makes this 0 for some valid choice of the subgradient s. And if we can do that, then we know that we found the solution. Okay. I'm going to try to do this piece by piece so we can see where it comes from. I can just tell you the answer and we can check it. Maybe we can try to just derive it ourselves without having to just start off with what it is. So let's suppose I'm at a, first I'll write this actually like this, beta I minus yi plus lambda si equals 0. Or maybe even I'll write it like yi minus beta I equals lambda si. So I have to satisfy this for all I equals 1 to 1. Or S is defined like up there. Let's look at a case now where yi happens to be bigger than lambda. If yi were bigger than lambda, then what could I do to make this equal to 0? I have to choose beta, so this is 0, where si is defined as its sign if it's non-zero, or otherwise it's 0. So let's just first try making beta I equal to 0. If yi were bigger than lambda, then if I make beta I equals 0, I get yi equals lambda times si. Well, when beta I is equal to 0, si can only be between minus 1 and 1. So I get yi equals lambda times something between minus 1 and 1. And if y was bigger than lambda, that can't work. So I know that I can't make beta I equal to 0. So beta I has to be non-zero, in which case si is going to be its sign. So let's suppose we take beta I to be positive. It seems a bit crazy we take it to be negative if y was already positive. So take it to be positive, I get yi minus beta I equals lambda. Right? And then obviously that just tells me I have to take beta I equals yi minus lambda. Okay, so we've satisfied the subgradient equation in this case. Let's look at the opposite direction. It actually is the exact same thing. In reverse, it tells me that I have to take, if yi is less than minus lambda, I have to take beta I to be yi plus lambda. In the last case, is that if yi happen to be between minus lambda and lambda, you can probably guess what's going to happen. Well, let's go back to trying beta I equals 0 again. If beta I is 0, I can take si to be anything between minus 1 and 1. And if beta I was 0, that goes away. So I have yi equals lambda times si. And if yi is already in the interval minus lambda to lambda, I can always choose an si between minus 1 and 1 to satisfy that. Right? So then I can just take it to be equal to 0. You convince yourself also that this is the only solution, just by going through the same subgradient arguments. I can't come up with any other one. So this is the solution to the optimization problem. We've proven it now. And this is sometimes called soft threshold. And we often write it like this. It's this soft thresholding map at level lambda applied to y. So it means I just take every component of y, and if it's bigger than lambda, I subtract out lambda. If it's smaller than minus lambda, I add lambda. Otherwise, I set it equal to 0. Okay. Let's take a break. You guys can think about that, and we'll come back and talk about some algorithms. the other option at this point actually that's really important. Okay, joke or test topics, which one comes first? Those test topics are not a joke, that's the other thing. Let's see. Okay, we'll try this one. Two cubic smoothing splines go to the gym. The first is linear beyond the boundaries and the second is cubic. The first is looking pretty big, so the second asks if he's on steroids. The first says, "Nah, bro, I'm all natural." remembered what a natural spline was, that would have been hilarious. What do you call a baby eigensheet? A lamb, duh. Okay. Some good ones there. Larry wrote this up on the board. Did you want to say anything else? On Monday, I guess we're going to give review sessions, so we're not going to cover new material. We're just going to field questions from the audience. These are the topics they'll be tested on for the midterm exam. The midterm exam is 1 week from today. We'll be in class. I don't think we're intending to make it terribly hard. It's supposed to be, don't worry about the level. And we're going to also release some practice questions, hopefully today or tomorrow, or not too soon after that. Okay, so I think just the level of homework questions is probably easier and shorter. That's what I would guess, but the same flavor. Kind of simple things to prove on these topics. Questions? Okay, back to the good stuff. We're going to talk quickly about first order methods. And then I may not get to the KKT conditions, but that's fine because we're going to come back to optimization in a few weeks from now. When we talk about minimax rates, I'm going to revisit optimization and tell you what the analog is in this setting. So I can hit the KKT conditions then. You won't need it between now and then anyways, unless you are stuck on a problem in your research, then you can come to office hours and you can ask. But here's just kind of a survey of the landscape for first order methods. We're going to talk about minimizing functions now, so actually algorithms to do so. We've seen all sorts of stuff like the properties, when we can do this, when there's a local minima. We've learned a bunch of good background material, and now we're going to talk about algorithms that you can implement in your favorite programming language, say. And we're going to talk about unconstrained minimization. So there's no constraint set here. If there is a constraint set, if I had something like subject to write, gi of x less than equal to 0 and lj of x equal to 0, like we have in the most general form of the optimization problem, we can just think about that as saying that x has to be in some set C. And everything I talk about actually, pretty much everything I talk about, you can also use to solve this problem by just projecting onto C after every step. So you make a step when one of these iterative algorithms, and then you project onto the constraint set. You find the closest point of the constraint set to your current iterative, and that'll work. Okay, so we're just going to consider unconstrained minimization for now. So here are the two, I say, canonical methods for doing minimization in this unconstrained setting. There's gradient descent and subgradient. I've already made a mistake. I always do this. We should be careful about calling it subgradient method, although I think a lot of people aren't, which is why I always write it as subgradient descent. And I'll explain to you why in a second. If f is differentiable, then I can perform the following steps, which you probably have seen before. They're very simple. I just start somewhere, I pick some x naught, and I repeat the following steps. I compute the gradient of f at my current guess, and I move in the direction of the negative gradient. So I'm at xk minus 1. I compute the gradient of my function at xk minus 1. I multiply by some number tk. Tk is bigger than 0. It's called the step size. And I repeat. I just continually move in the direction of the negative gradient. Okay, how do we choose step sizes? I'll talk about in a second. If f is not differentiable, if we try to do non-smooth minimization, then I can use subgradient method, where all I do is instead of taking the gradient of f at the point xk minus 1, I just choose a subgradient of f at xk minus 1. So here, gk minus 1 is just any subgradient of my function f at the point xk minus 1. And why have I called that method versus descent? Well, this one we can actually prove that as long as I choose tk correctly, this is the descent method, which means that the value of the criterion keeps decreasing as I traverse through these iterations. So f of xk is always less than or equal to f of xk minus 1. It makes intuitive sense because I'm moving in the direction of the negative gradient. As long as I don't move too far, as long as 2k is not too large, it will be a descent method. Subgradient method is not a descent method. Even if we choose tk correctly in some sense, it can still have the property that the criterion gets bigger as we make a step. So actually what we do in subgradient method is that we, at every iteration, we're going to keep track of this thing which we call xk best, which is just the argument over all I from 1 to k of f of xi. So we just keep track of the criterion value over the last k iterations, and we just make sure to remember which guy had the best criterion value. Because as we proceed, it could be the case that we get worse. Okay, so that's one difference between these two methods. We'll talk about that in a second, yeah. So the first difference between these two methods is the step size choice. So in both methods, I could choose the step size to be some fixed value t. Okay, in graded descent, actually, what happens now, so I'll write it as graph. Provably, and actually the proofs in the notes, we may go over this when we come back to optimization, like I said, in a few weeks. Provably, as long as t is small enough, so I'll write t less than or equal to 1 over L. L is the Lipschitz constant of the gradient. So that detail is not important, but you can just think about t is small, then this converges. With a fixed step size. Okay? Here's the difference for subgradient descent. With subgradient descent, it's always suboptimal. For any t that's positive, if we take a constant step size, it's always suboptimal. And I don't remember if I have the proof or the bound in the notes, but I can show it to you if you want.
So the step size, you fix the step size or you
Yeah, if the step size is fixed at some constant, then it's suboptimal. And the amount by which it's suboptimal, we can also specify. You can say the limit of the function as I track the best subgradient iterate, as k goes to infinity, is less than or equal to f star, which is the optimal criterion value, plus something that depends on t, and ends up being this, I think, unless I have a bad memory. It's g times t squared over 2, where this is the Lipschitz constant of the function. Okay, but that particular constant is not important. It's just telling us that this is never going to go away if I take t to be constant. Okay, one difference between the two methods. So how do we choose step sizes beyond the fixed case? Well, actually, there is in some sense, a better choice for both methods in the fixed case. And I'll talk about gradient descent first in its choice. And that one is called backtracking. And this is a way to choose that step size tk adaptively at each iteration. With every iteration, I'm going to actually kind of aggressively choose a step size rather than just choosing some fixed value. We don't have an analogy of backtracking for subgrading method. It doesn't exist. So I'll tell you about how to choose its step sizes in a different way than you would with a fix in a section. But I wanted to make sure I covered this because it's on your homework too. I think you're supposed to implement gradient descent backtracking for the mean shift problem. So backtracking within each iteration, so at each iteration, okay, we're going to do the following. We're going to start with our guess at the step size t to be something. Let's just say 1. I could choose this to be 10. Doesn't matter. I just initialize it to some value that's large enough that I'm not going to be starting at too small a step size. And then I'm going to repeat the following. I'm going to check whether or not the function, I'm going to drop the k notation just to make it simpler. We're at the point x, and I'm going to try to move from the point x with the proposed step size t. I'm going to check the proposed update. So I'm going to check going from x minus t times the gradient of x. Look at its criterion value. If it so happens that this is bigger than what I get by essentially this right-hand side looks like a line that emanates through x with slope negative gradient of f of x, and I've degraded the slope by alpha. I'll draw a picture for you in a second. But while this is true, this is saying that I haven't made as much progress as essentially I would with the linear extrapolation from f. I'm going to shrink the value of t. Okay, so backtracking takes 2 parameters. First, we specify some value of beta between 0 and 1. That's the amount by which we shrink our step size at each iteration of backtracking if we haven't made much progress. It takes a second parameter, alpha, which is between 0 and a half. Okay, let me draw for you a picture. I think it's going to help. Picture. So first of all, let's just remember that let's suppose that I'm going to move from x in this direction, right? I'm going to move from x in the direction minus t times the gradient. So I want to evaluate my function at this proposed update. So I'll take a linear approximation to my function. Right, so the linear approximation of my function, I'll write it as maybe f. I'll write it as f lin. Right, at any point y, that linear approximation is going to look like f of x plus the gradient of f of x transpose y minus x. And in particular, if I look at the point y equals x minus t times the gradient of f of x, I get that the linear approximation to my function at x minus t times the gradient of f of x is equal to f of x plus, well, what's y minus x? It just ends up being this, minus t times the gradient. I'm taking that transpose the gradient, so I get minus t times the norm of the gradient squared. So let's suppose here's our function, and I'm at the point x, and I want to think about taking a step. Let's say here's x, and I want to take a step to here, which is x minus t times the gradient. And so what I do is I'm saying I look at this linear approximation to the function at this point. However, that's way too ambitious to ask for the value of the function to be below the value of this linear approximation. In fact, we know if f is convex, that can't happen. Right? You know, the tangent line is always going to underestimate the function. So that's why we do this, backtracking. We multiply this by alpha. We degrade the slope by alpha. Where alpha is some number between 0 and 1/2. So all it does is it puts an alpha right here. So that just takes this line and it makes the criterion less ambitious. And so in particular, I evaluate the function on this line, and I evaluate the actual function, and I see if I've actually been able to beat this relaxed linear approximation, then I've taken a sufficiently far step size, and I'll stop. Okay? Yeah.
How come we use the back?
Good question. Well, in a sense, making it bigger, you can't really control. So let me extend that picture out and maybe it'll make sense. The point is that you start with a really big step size. So let's suppose I took a step size that put me out here. Then I'm not going to meet the backtracking exit criterion up here, right? Because the function is way above the line. And so I shrink it until basically, suppose beta was 3/4. Then I try this point, and it doesn't work. And I try this point, and maybe it works, and I stop. Right? And so if we take this initial choice large enough, then we're expecting not to pass for the first few backtracking checks. But as I shrink it, it'll pass eventually. If I take it larger, if I allow myself to increase it, then there's no telling as I increase it that I'm ever going to actually meet the exit criterion. It's really only in the other direction that at some point it'll be the case that I'm able to have the function lie below this line. The risk is that if I take this to be too small, then I'm kind of shooting myself in the foot. If for my particular problem I always took this to be something that always passed the backtracking exit criterion, then we're not really getting the full advantage of backtracking, which is to start with something big and be greedy and then decrease it until we have this condition. Did you have a question?
No, because it's coming on what he says. Maybe even if like in practice you will never know if you've chosen it large enough first of all, or too small or too large. So maybe you can start with 1, and if it's above the function, then maybe you can increase it by 2 and keep going until it actually really goes below until the linear approximation goes below the function.
Yeah, that's not unreasonable at all. You're right. So you could do something like you could check whether or not, if it's met the first iteration, you could try to increase it and see if it's still met, and you can increase it until it's not met. And go back to the last one. But if it's not met at the first iteration, you keep shrinking it, then you're kind of already adjusting for the fact that you don't want for it to be too small, right? Because as long as beta is not too small, if it's something that's closer to 1, then you're just shrinking it kind of carefully away from the big step size. But you're right, you could probably go back in both directions. Kind of sounds more like a binary search kind of already at this point. Did you have a question?
Well, Ryan, you said you meet the criteria and you stop. You can stop at step, but you're not
Yes,
stopping.
sorry. You stop this inner loop and you stick with this value of t. And so that's the step size that you perform in grading. So thanks for clarifying. Then I go and I use that t up there and I take a full gradient step. The next gradient update, I do this inner loop to find the step. Usually you start at some pre-specified value of t. Yeah, some large pre-specified value of t. So backtracking is quite a useful thing, yeah.
Do you take this up first and then you do this move? Or or you keep doing it until we get it to work? And then
Yes, you don't take the step first. You do this until you find a value of t that satisfies this condition, then you take the step. And so I have some pictures in the notes. I have some examples where it's on page 16 if you want to take a look at it real quick. I have a two-dimensional function, and I put down the contours of that function. And I start with three choices of step sizes. One that's too big, one that's too small, and one that's kind of just right. And those are all fixed step sizes. So I just chose some fixed t here. And the one that's too big actually diverges. So remember I said here that the fixed step size for gradient descent it has to be small enough for it to converge. So we see in this picture it actually diverges with a too large step size. If it's too small, it'll converge, but it converges way too slow. And so in this picture, we've taken hundreds of iterations and it's really slowed down. And if it's just right, it converges fine, but that's often hard to find in practice. The just right depends on something like the Lipschitz constant of the function, but sometimes you won't know. And so in the picture in the middle of the page, I run backtracking. It's a pretty standard backtracking plot. I haven't chosen alpha and beta carefully. I always choose alpha equals a half. So the way I tend to think about backtracking is that now you've just reduced to choosing one parameter, and that's beta. You can just fix alpha equals a half. And so this picture I chose beta equals 0.8. And in something like 8 or 9 steps, you can see it gets very close to the number. So it tends to work quite well. I'm going to have to tell you real quick what to do with subgradient descent. Remember I said I'd tell you for each method what to do. I'll just write down the answer. For example, take it to 1 over k. So if you have any choice of the tk's that satisfy this property, that their sum is infinite, but when I square them and sum them, it's finite, then under this condition, we can prove that actually subgradient descent converges to the optimal solution. So here is a choice of such a prescription. Just take it to be 1 over k. The difference between subgradient descent and gradient descent is that we don't have adaptive schemes like we do for gradient descent in the subgradient world. Even though we have non-fixed choices of step sizes, they're still pre-specified like this one. Did you have a question?
You sort of answered it, but I guess I was also, so why do we, dumb question, why do we not have adaptive schemes?
Backtracking schemes?
Yeah, like why don't, or yeah, line searching.
Line searching. Yeah, it's a good question. Well, so for one, the proof that subgradient descent converges is very different from the backtracking proof. If you're interested, it's the gradient descent proofs in the notes. The subgradient descent proof is in the optimization notes, but they don't kind of live in the same realm, those two proofs. So it's not at all obvious that something like backtracking would work. The other thing is that it becomes unclear what to put here, right? In the backtracking analogy for subgradient descent. If I put a subgradient in there, then it's I could exit that condition rather fast or rather slow depending on what I put in there. There's a different choice of subgradient. So I'm not sure there's a natural extension. But at a philosophical level, I don't know that there's a reason why we don't have adaptive methods. It's just that at this point the proofs don't work for adaptive methods.
So people just do kind of what you wrote, the one.
Yeah. This is summable or square summable, but not summable. That's the name of the rule. Diminishing step sizes. This is probably the most common choice.
Yeah, if your function is like differentiable except from a very small set, then would it be safe to just take the gradient and do backtracking?
Good question. Yeah, so there are some hybrid schemes which, like for example, if you're looking at hinge loss and it's only non-differentiable at a certain point, that kind of allow you to use the gradient when it's differentiable. But as far as I can tell, I don't know that there's anything provable about such schemes. It just seems to be common practice that if you have a function that's only non-differentiable at certain points, then you would just run gradient descent as prescribed, and if it becomes non-differentiable, then you choose a subgradient. So the last thing I say, I know the class is over, I'll just give you a taste for what's to come. Convergence rates. So we'll talk about this later in the course. These two have very different convergence rates. I'll write them down. This one is order 1 over k. This one is order 1 over the square root of k. What that means is that after k iterations, I can expect the error between the iterate, the kth iterate, and the optimal criterion value to be like 1 over k times a constant. That constant is the distance between where we started and the optimal value. Okay, so in other words, the error that I'm making scales as 1 over the number of iterations. That's how fast this converges. With subgraded descent, converges as 1 over the square root number of iterations. It's actually quite a big difference. When we flip this around and talk about how many iterations you need to achieve a certain error, like I asked you how many iterations you need to achieve an error of epsilon, you see this is 1 over epsilon iterations. This is 1 over epsilon squared iterations. And so that is a very big difference to make epsilon smaller and smaller. Now what we'll talk about later in the course is, this is a very natural question, especially when we talk about rates. You could ask, is this optimal? For differentiable functions, is this optimal? Can I do better than this? And for non-differentiable functions, is this optimal? Can I do better than this? Well, it's maybe not a very positive result because we know that subgraded descent can be slow, but actually this is optimal. So this guy is optimal in the sense that if I have a non-differentiable convex function, I can't hope to do better than that rate. It's about as good as it gets, so you might as well use subgraded descent. If you have an arbitrary non-differentiable convex function without special structure. And we'll either prove this one or the other one, I haven't decided yet. This one, kind of intriguingly, turns out to be non-optimal. So this is not the best we can do. So for a smooth convex function, it turns out you can do better than 1 over k. That's not the best you can do. The best rate is actually 1 over k squared. That's the lower bound. The good news is that there is actually a concrete method that achieves this. This is due to Nesterov in the 1980s, and it's called acceleration. So they actually take gradient descent and we accelerate it using this kind of clever scheme. It achieves the optimal rate of convergence. We'll talk about that maybe in a week or a couple weeks.